Today we're going to be talking about how to find global extrema of a multivariable function, given that that function has been defined for some domain D. And in this particular problem, we've been given the function f of xy is equal to x squared plus y squared plus x squared y plus 4. And we've been told that the domain on which we're supposed to test for global extrema is absolute value of x less than or equal to 1, and absolute value of y less than or equal to 1. Now let's pause for a moment and talk about a single variable function. Remember when we were looking for global extrema and we had a single variable function? And what we said was that if the function here is some curve in space like this, and we were given a domain, let's say between this x value right here and this x value right here. Our goal to look for global extrema in that interval was to identify critical points, so those critical points would have been here and here, and we would test those critical points to see the value of the original function at those critical points, but we would also test the endpoints in that interval, and based on the values of the endpoints and the critical points, we would identify a global maximum and a global minimum. So this value, for example, here would be the global maximum because it's the highest value the function attains in this interval. And if one of these points here was lower than the other, we would identify that as the global minimum in the interval. If these 2 points had the same y value when plugged into the original function, we would say that the 2 of them together constituted local minimums because there was no global minimum where one value was less than the other. Well, when we're talking about a multivariable function, it's the same kind of concept. We need to test everything in the interval, but we also need to test the endpoints, except that when we're dealing with a multivariable function, we don't just have an interval for x, we also have an interval for y. So if we graph the domain of this multivariable function here on an xy coordinate system, and we call this axis x and we call this y, and then we're defining this domain, we said the absolute value of x had to be less than or equal to 1. That means x can be any value between -1 and +1, because if we plug -1 in here for x, that'll still satisfy the inequality. So we know x is between positive and -1, let's say -1 and +1. Similarly here for y, we know y is between -1 and +1. So if we say -1 here and +1 here, then we say that our domain is this area here defined by the square, these 4 lines, these 4 line segments, y equals -1 and y equals +1, and x equals -1 and x equals +1. So we have the square for the domain. Similarly to our single variable function, what we want to do is test for all critical points inside this square. We want to identify any critical points inside this square, plug them into our original function to find their value, but then we're also going to need to test the 4 edges of our domain and the 4 corners of our domain. So there's really going to be 3 steps: critical points in the middle, the edges, and then the corners. To find the critical points on the inside, we're going to follow the same process we use for finding critical points when we're talking about local extrema, and that's just to find the first order partial derivatives of our function with respect to x and y. So we have the first order partial derivative with respect to x, which is going to be equal to 2x plus 2xy, and then our first order partial derivative with respect to y, which is going to be 2y plus x squared. Now, in order to find critical points, we need to solve one of these equations for one of our variables. We can start with this second one here. It doesn't really matter how we go about it, but in this case, I'll start with this second equation, and I'll try to solve it for y. So I'll subtract x squared from both sides, and I'll get 2y is equal to -x squared. Then I'll divide both sides by 2 and get y equals -1/2 x squared. Now I can plug this value, -1/2 x squared, into my first equation for y to get an equation that's only in terms of x. So when I do that, I'll get 2x plus 2x, and here's where I plug in for y, -1/2 x squared, and I set that equal to 0. Now I have an equation that's just in terms of x, and I can solve this for x. So when I simplify, I'll get 2x here for my first term. My 2's will cancel here. I have x times an x squared, which is going to give me an x cubed. I need to bring this minus sign in front, so I'll get minus x cubed is equal to 0. To solve this for x, I'll just factor an x out into the front, and I'll get x times 2 minus x squared is equal to 0. And if I set both of these factors individually equal to 0, I'll get x equals 0, And if I set 2 minus x squared equal to 0, I'll add x squared to both sides and get 2 equals x squared, and then take the square root of both sides. I get x equals positive or negative square root 2. So I have three values for x, 0, and positive and negative square root of 2. However, just like before when we were dealing with a single variable function, I need to see whether these x values lie within the domain that I'm testing for. And positive and negative square root 2 do not lie within the domain. They don't satisfy this inequality, absolute value of x less than or equal to 1. So these are both values that I don't need to consider, and x equals 0 is the only value I'm interested in. I need to find a corresponding y value that goes with this x equals 0 value. So I'll go ahead and plug this into this equation right here, and when I do, you can see I'll get negative 1/2 times 0 squared, or just 0 over here on the right, so I'll get y equals 0. That means that my only critical point inside of my square here is the point 0, 0. Now, just like with a single variable function, when I found a critical point, like if I found this critical point here, I would just plug this point into my original function to find the value at that point. I'm going to do the same thing here. I'm going to plug 0, 0 into my original function. So f of 0, 0, my x squared term will go away because it's 0, my y squared term will be 0, my x squared times y term will be 0, and I'll just be left with 4. So f of 0, 0 is going to be 4. Let's go ahead and put that down here. F of 0, 0 will be 4. And I can go ahead and draw a picture of that inside of my domain here. I'll graph my point 0, 0, and I'll say that the value there is 4. Now, in the same way that for a single variable function, I tested my endpoints, here I need to go ahead and test my corners and my edges. We'll start with corners first because that'll be easier than doing the edges. So let's start with this point right here. We'll call this point 1, 1 because here x is equal to 1 and y is equal to 1. So we have a point 1, 1, and we'll plug that into our original function, f of x, y. So f of 1, 1 is going to be equal to 1 squared gives me 1, plus 1 squared gives me 1. 1 squared times 1 is 1 plus 4, and I can see that this is equal to 7. So I'll call this point here a value of 7. Now I need to test the other 3 points. I'll do f of positive 1, negative 1. That's going to be equal to 1 plus 1 minus 1 plus 4, in other words, 5. So the value at this corner right here is equal to 5. I'll do now my point negative 1, negative 1. So f of negative 1, negative 1 is equal to 1 plus 1 minus 1 plus 4, or 5. So I can indicate that this value here is 5. And my last point, f of negative 1, positive 1, is going to be equal to 1 plus 1 plus 1 plus 4, which is going to be equal to 7. So the value at this corner is equal to 7. Now I've done the critical points on the inside and I've done all 4 of the corners. I need to address now the line segments that connect the 4 corners. Now before I get to testing the edges of my domain here, let's go ahead and label these line segments. Let's call this line segment d sub 1, we'll call this d sub 2, this line segment we'll call d sub 3, and this will be d sub 4. We're going to be looking to identify an equation that describes this line segment in 3-dimensional space. Then we're going to look for critical points along that line segment, and then plug that critical point into our original function to find the value there. So let's start here with d sub 1. We'll say d sub 1 here. What I want to do is realize that all along d sub 1 here, the value of y is going to be negative 1, right? This is essentially the line y equals negative 1. So the way that I can find an equation that represents this line segment is by replacing y in my original function with negative 1. So instead of f of xy, I'm going to say f of x, comma, negative 1, replacing y with negative 1. When I simplify that equation, I'll get x squared. Plugging in negative 1 for y, I'm going to get plus 1 here. Then because I plug negative 1 in for this y right here, I'll end up with minus x squared, and then I'm going to have my plus 4. My x squareds will cancel, and my equation just becomes 1 plus 4, or 5. Because I get a constant here, this tells me that the value all along my line segment, d sub 1, is going to be equal to 5. So let's just say that this is equal to 5 here. Let's talk about d sub 2. It'll start getting a little more complicated. So all along the line segment d sub 2 here, my value of x is equal to 1 because this is essentially the line x equals 1. So what I want to do is in my original function f of xy, I want to replace x with 1. So I'm going to say f of 1 comma y. And therefore my equation will simplify to 1 plus y squared plus y plus 4. And when I simplify that, I'll get y squared plus y plus 5. Now notice I didn't get a constant value here. This is a function that represents the line segment d sub 2. What I need to do is use it to find a critical point along this line segment. And the way that I'm going to do that is by taking the partial derivative of this function with respect to y. Now I'm taking the partial derivative with respect to y because y is the variable here that remains. Because I have 1 comma y and this is the variable that's left, I know that my partial derivative is going to be with respect to y. So I'm going to say the partial derivative of f with respect to y of 1 comma y is going to be equal to 2y plus 1. Now in order to find the critical point, I need to set this equal to 0. I'm going to subtract 1 from both sides and I'll get 2y is equal to negative 1. Dividing both sides by 2, I get y equals negative 1/2. Remember now that all along this line, x is equal to 1, so it tells me that my critical point along this line segment is at the point 1 comma negative 1/2. So if I graph that critical point, I have 1 negative 1/2, that's going to be right here. This is the critical point along the line segment d sub 2, and I just need to test this critical point in my original function f of xy. Before we do that, let's go ahead and find the critical points along d sub 3 and d sub 4 if they exist, and then we'll test all of them at one time. So we'll box this for now so we remember to come back to it later. For now, let's talk about d sub 3, so we'll say d sub 3. Remember, along this line, y is always equal to 1, so we're going to say f of x comma 1. We're going to replace y with 1. That's going to be equal to x squared plus 1 plus x squared plus 4, and when we simplify, we'll get 2x squared plus 5. Because x is our variable that remains here, we need to take the partial derivative of this function with respect to x. So we'll say partial derivative of f with respect to x at x1 is going to be equal to 4x. Now I want to set this equal to 0 and solve for x by dividing both sides by 4. I'll get x is equal to 0. So that tells me that my critical point for the line segment d sub 3 is at the coordinate point 0, 1, because I know that all along that line segment y is equal to 1, so I have x equals 0 and y equals 1, and that point of course is right here, so that critical point is at 0, 1. We'll go ahead and box that one and save it for later, and then finally my line segment d sub 4, so we'll say d sub 4. Along this line segment, x is always equal to negative 1, so we'll say f of negative 1 comma y, and we'll replace in our original function x with negative 1, so we'll get here positive 1 plus y squared plus y plus 4. This is going to simplify to y squared plus y plus 5. Now realize here that this is the same equation that we ended up with over here for the line segment d sub 2, y squared plus y equals 5. Remember that we took the partial derivative with respect to y because y was the variable there that remained, and that's the same here. Y is the variable that remains. So we know our partial derivative is going to be the same. We're going to get 2y plus 1. We're going to set that equal to 0 and find that y is equal to negative 1/2. We know that all along this line segment, x is equal to negative 1, so that leaves us with the point negative 1, negative 1/2, which we can go ahead and graph here as negative 1, negative 1/2. That critical point is right there, and we can go ahead and box this. So now we have here 3 critical points that we need to test in our original function f of xy. Let's go ahead and do that. We'll test 0, 1 first. We'll say f of 0, 1. That's going to be equal to 0 squared is just 0, plus 1 squared is 1, plus 0 squared times 1 is still going to give me a 0, so I have just plus 4. That's going to be equal to 5. If I test negative 1, negative 1/2, I'll get f of negative 1, negative 1/2. When I plug that in, I'm going to get negative 1 squared or positive 1. I'll get negative 1/2 squared or positive 1 fourth. Then here, x squared will give me a positive 1 times a negative 1/2. That'll give me a minus 1/2, and then plus 4. I'll get 1 plus 4, which is 5, plus 1/4 is 5 1/4, minus 1/2 is 4 3/4, so 4 3/4. And instead of making this fraction 19/4, we'll leave it as 4 3/4 because this will be easier for us to compare to our other values like 5 and 4 here. Now finally, let's plug in the point 1 negative 1/2, so f of 1 negative 1/2. When we plug that in, we'll get 1 plus negative 1/2 times negative 1/2 is a positive 1/4. Then we'll get minus 1/2 and then plus 4. That's exactly the same arithmetic we ended up with here, so we know that our result is going to be 4 3/4. So here's how we put all this information together. We have this critical point which is on the inside of our square that we have to consider here. We have 3 critical points along the edges that we have to consider, these values right here. And we also have 4 values on the corners that we have to consider. So it's the corners, the critical points along the edges, and the critical points on the inside. We want to put all this information together and then identify global extrema. So here's what we have. Our smallest value is 4, right? We have values of 4, 4 3/4, 5, 5, 5 here, and 7. So we say that f of 0, 0 is equal to 4, and then we can go ahead and erase this here. So that's our smallest value. Then we have 2 critical points that have a value of 4 3/4. So we'll say here f of, notice that these 2 points are negative 1 negative 1/2 and 1 negative 1/2. So the y values are the same. The x values are positive negative 1. So we can list this as positive negative 1 comma negative 1/2. These 2 critical points have a value of 4 3/4. We have 3 critical points that have a value of 5. F of 0, 1, so we'll say f of 0, 1, which is equal to 5, comma, we have these 2 coordinate points here which are corners. This is 1, negative 1, and this is negative 1, negative 1. So again, the y value there is the same. Both of the y values are equal to negative 1. The x values are 1 and negative 1. So we'll say f of positive negative 1 for x and negative 1 for y. Those values are all equal to 5. Finally, we have 2 corners, 2 critical points, where the values are equal to 7. This is the point 1, 1. This is the point negative 1, 1. So notice here that our y values are the same. They're both 1. Our x values are positive and negative 1. So we'll say f of positive negative 1, comma, 1. Those are both equal to 7. Now to identify global extrema, we're looking at the values over here on the right-hand side. Our smallest value is 4, our largest value is 7. So we have 1 critical point at 0, 0, which is equal to 4, so we can say that we have a global minimum, or a global min, at the point 0, 0, and that's equal to 4. Then we have 2 points here which share the maximum of the function, f of 1, 1 and f of negative 1, 1. I don't like to call those global max because there's not one point that exclusively is the maximum of the function on this domain. So I like to go ahead and just say maxima of the function are going to be at the points positive negative 1, comma 1, and those critical points are going to have a value of 7. So that's your final answer, and that's how you find global extrema of a multivariable function, given that that function is defined on a domain D.